Hi, this is Jeff Coronado. I'm a licensed structural engineer at JCSC, and this is Bridging the Gap. So the title today of the tutorial that we're doing, wind, get my pen out here. So we've got the titles here, wind, CC, that's component and cladding, a stud wall with a parapet, and what we're looking at in particular is the load path. So we've got wind, component and cladding, stud wall with a parapet, and we are looking at the load path. All righty. So the question that had kind of come in, and we're kind of surmising here, I'm sorry, not surmising, but kind of paraphrasing. What is the load path for the out-of-plane wind pressure on a stud wall with a parapet? All right, so let's jump into our detail. So the detail is shown here. You know what? Let me see. Yeah, that's probably big enough. Make it a little bit bigger. All right. So, oh, but then I kind of, let me see if I can scoop this up a little bit. All right, so in essence, here's our detail. So we've got a parapet wall assembly which has two studs. So it's a two-stud assembly. And sure enough, here's one stud, and I'll show it with this red line segment. I'll use yellow to denote the floor, and obviously not quite to scale. But here is, right here is a double top plate. Get rid of it. But there's our double top plate. And so here's the floor. And so here's one stud element. And then I'll use, let me use blue maybe to show the other stud. So there's another stud that then goes again from the double top plate past the roof assembly, and it creates this parapet up here. So we've got a two-stud assembly. We've got a stud that's full height from floor to floor or floor to double top plate, and let's say this might be a ceiling, probably is a ceiling right across here. So from the floor to the double top plate, and then from a double top plate onto the top to create this parapet. All right, wind, component and cladding pressures induces a horizontal out-of-plane force on the wall assembly, sure. So one of the forces that we need a wall assembly to resist is the out-of-plane force due to wind. So let me sketch that in. All right, so we've got, and these loads, the wind load is reversible. Remember, wind can create a positive inward pressure into the wall, as well as a negative suction pressure, which pulls the wall away from the structure. All right, so here's our wind out of plane pressure that we need to have our stud assembly be able to resist. So let me see, do I want to, let's see if I should scroll down here. You know what, yeah. Okay, let me scroll down here a little bit. So what we have for the full height stud, let's model the full height stud as a simply supported beam. Right, there's the full height stud. So that's one of the two studs that we have. Let me use a different color. Let me use red to model the parapet portion of the stud, that cripple stud. Call it cripple because it's not quite a full height stud. You know what, so let me draw this a little bit shorter so that it's a little more apparent that's it. And you know what, let me while I'm doing this, let me say something else. Um, it's almost a word of caution. I know that sometimes it's easy to kind of jump around in a tutorial and extract the explicit information that you're looking for. And gosh, I would strongly caution you against that. Try to bear with me, try to stay with the full tutorial, because if you think about it, you're shortchanging yourself, right? The idea isn't for you to jump into a tutorial, get the one numerical answer that you're looking for, and then be done with that, because then you're really not learning. You're shortchanging yourself. What you want to do is try to extract the thinking process, the structural engineering thinking process that I'm sharing with you. Because if you're able to extract that a few times in the tutorials that you listen to, eventually you'll find that you stop needing to be listening to tutorials, to watching tutorials, because you start grasping the thinking process that goes into structural engineering, right? So try to grasp the process of the thinking just as much as the numerical answer that you're getting out of this. But okay, so I've drawn the parapet portion of the stud. So again, these are simply supported because that's typically how we assume studs to be. Typically, it's practically not feasible to create moment connections with studs. So almost always you'll find studs, we need to model them as simply supported elements. So we got the full height stud here, modeled as a simply supported beam. And then the second stud that creates that parapet. Oh wait, I didn't draw this right. I didn't draw this right, did I? Because this is a simply supported element, but it has an overhang. Right, remember that? Let me see if I can. Oh, this sketch right here, right? So that second element, remember that the second element right here is supported right here, and it's supported here at the roof with the roof framing. So that's where the supports will be for this parapet stud. So we got a support at the end, and we got a support somewhere along the length of that stud element, which is right here. Righty, so with that, let me get rid of this and scroll back down. Okay, so where are we here? I think right now we're looking at somewhere in here. So we have two simply supported beams with a shared support, right? So the shared support is right here, right? So there's our shared support. We'll call the shared support R2, okay. Sounds good to me. I can do that. We'll call this R2, which is the resultant of R2 from the left. Okay, so we'll call this little guy here R2 left, right? Because part of, yeah, I'm running out of space. Part of the reaction that goes into the support comes from this full height stud and the wind load that acts on it. And part of this reaction, part of this load that goes into this reaction is coming in from the right side, from that parapet side. So we'll call that R2 right. So R2 is derived from the R2 left and R2 right. Okay, all clear? If you aren't, by all means, send me an email. We'll try to clarify. Some of these things have already been covered in other tutorials. So again, feel free to ask, but they have been covered in other tutorials. The determination of component and cladding wind pressures, other things have been covered in other tutorials. So just feel free to send me an email with anything that you're not understanding, and we'll certainly try to clarify these things for you. Okay, let me see here. All right. Let me see if I can get rid of this mark here. Okay, so just a little bit of a tease here. Let me switch over to So does R1 equal R2 left? So this is R1, right? This is our R1 reaction. All right, a little bit of a tease. Does R1 equal R2 left? Remember, R2 left was this reaction here. So think about it for a second. And if you're saying yes, it would be equal, I think that would be a fair answer. Provided this wind pressure is uniform across the full length of the stud, no reason to believe it's not, then R1 would equal R2. So, okay, fair enough. How about the second question? Does R2 equal R3? So R2 is this, right? That's the addition of R2 left and R2 right. Would R2 left and R2 right equal, and here's our R3. R3, remember, is the reaction that goes into the roof. So if you want, we can scroll up and take a look at it physically. What we're asking is the reaction from the wind, the reaction that occurs, let's see here. So we've got this wind pressure. You know what, instead of drawing it as a line, let me draw it. We've got all this wind pressure, and then we've got a reaction here at this double top plate, which is what we're calling R2, and we've got a reaction at the roof, right? And that's what we're calling R3. Does R2 equal R3, right? That was the question that we had. So let me see if I can scroll back down. Does R2, right, does R2 equal R3? So that's this question right here. Does R2, this one here, equal R3? So think about it for a second. And hopefully you're realizing that the answer is no. R2 does not equal R3. The reaction that we have due to the wind pressure at that double top plate at R2 would not equal the reaction that we have at R3, which was at the roof line. Okay, so let's scroll down here. What do we have? Where does R2 go? Ah, and I just lost our diagram. Well, let's see if I can get our diagram back up here. So remember, we have a full height stud. Let me draw this a little bit bigger. A full height stud, a cripple stud with an overhang. And this was R2. So where does R2 go? So this is kind of a blow up of R2. So this is the cripple stud that creates the parapet. Here's the full height stud. And this, in case we didn't, and I didn't mention that, that's a brace, by the way. So let me see if I can go back up the screen here. And you can still kind of see right here in the actual detail, this element, this element right here is a brace. That's a diagonal brace that spans between the top plate here, and it goes up and connects to the roof framing up here. All right, so let's go back. Let's see if I don't know. We go back to our sketch here. Okay. And let me get rid of some of these marks. I don't think we need this one or this one or this one. Okay, so we've got that cripple stud creating the parapet right here, the full height stud, which is this one, and then we've got the brace right here, right? Now R3, I'm sorry, not R3. Where is this labeled R3? Looks like a 3. Let me erase that so that I don't get confused here. This should be R2, right? So R2 is going into this double top plate, right? So the wind pressure from the stud is connected to the top plate. That wind pressure goes from the stud into this top plate. The wind pressure goes from the cripple stud that creates the parapet also that stud is connected into the top plate so that wind pressure goes into this double top plate. If you're not clear on what a double top plate is, by all means, shoot me an email, right? Any of these terms, stud, cripple stud, and some of that may be covered in other tutorials, but by all means, feel free to ask. So they go into the double top plate. Now, the question is, can the double top plate resist that pressure? Well, the answer is, in most cases, no. Unless it's a very short wall, the double top plate would not be able to resist that pressure. If you think about it for a couple of minutes and that isn't clear to you, send me an email. But the double top plate, for most situations, would not be able to resist that pressure. Hence, we need a brace right here. And that's why we have the brace that we've added. So that brace, we need to determine by calculation, by the forces that go into that brace, how frequently we're going to space that brace, whether we're putting braces at, I don't know, 4 feet on center, 6 feet on center, 8 feet on center, that needs to be determined. There was something I wanted to say. Okay, so let me see if I can erase, let me get rid of all of this. So now that we've determined that the horizontal reaction here, R2, goes into the double top plate and the double top plate itself can't resist it, then we know that R2 needs to go into the brace. Okay, so R2 goes into the brace. Now, the important thing there then is, let me get rid of this sign. The important thing there is that then you as the engineer have to design some kind of connection, some kind of connector right here to ensure that you can transfer the force R2 from this double top plate into that brace. So you need to provide a connection there that'll be able to, that is adequate to resist this R2 force. Now, when you're checking your brace, and that's what I'm trying to alert you to that fact right here. Remember that the force in that brace is not an R2 force. It's amplified because of the angle that the brace is at. If that brace is at about a 1-to-1 angle, which is what we tend to shoot for, then that amplification is 1.4. If the amplification isn't clear to you, send me an email and we'll try to clarify it for you. But the force that's in that brace is an amplified force. It's not R2. It's amplified by the angle. And also keep in mind that the brace itself is unbraced. It's fully unbraced, unless you take steps to brace it, but typically it's unbraced. So keep that in mind when you're designing the size of that brace. Let me see if I can scroll up here. Now, if we look at the top, let me scroll back up here. So now we've discussed the force that goes into this brace here, right? Remember that this is also reversible, right? Remember, the wind pressure can be what we call a positive pressure, which means it blows into the structure, or it could be a negative pressure. It pulls away from the structure. So depending on whether we're looking at the condition where the wind is blowing in and it puts the brace in compression, or the wind is pulling out and it puts the brace in tension, but we have to account for both situations. Now what we want to do is look at how this force that's in the brace resolves into the roof framing above. Because that was the initial question, right? Is what's the load path? So we need to get the force out of the elements and take it and complete the load path. So with that in mind, let's again scroll down. And now we're looking at the top of the brace. Actually, you know what? Let me erase this. Erase this, and this. Okay, so we'll leave R2 there, right? Right, so remember that the force we have in the brace is reversible, and it's an amplified, so I'm just going to say alpha. It's an amplified R2, maybe by 1.4 if the angle's around 45 degrees, but it's an amplified force R2. Okay, so we get the force coming up here. In case you don't know, use, no, you know what, I'm going to use yellow. This element right here, this component is called a block. If that's not clear to you, send me an email. But that's a block. We're connecting this brace, it's hard to tell, but we're connecting this brace to the block with nails. So you need to make sure that you have provided enough nails that have the capacity to be able to resist the amplified force alpha R2, to resist alpha R2. And that'll get you the force into the brace. Again, the force in the brace has a vertical component to it, as well as a horizontal component to it, right? Let me clear off the block so that, and you know what, let me zoom in a little bit. By zooming in, actually I get away from those arrows, and that's fine. Because what I want you to see is that there is a nail shown here, right here, that's connecting the block from this here is the wood structural panel. This is the diaphragm. That's kind of considered home base, if you will. Once we get our loads into the diaphragm, then we're done. We've resolved our forces. So that connector, that nail that's circled there in black, is what transfers the horizontal force from the block into the diaphragm or the wood structural panel sheathing. However, that nail can only transfer the horizontal component. And in terms of the capacity of that, that's something that's covered in another tutorial. So you can take a look at that so that you can see how to resolve forces into the diaphragm. The other part that we don't want to lose track of, let me see if I can. Okay. That we don't want to lose track of is this vertical force, right? Let me compare with red. We've got the vertical force, which is the vertical component of the alpha R2 force. That vertical force goes into this block, right? Now, again, those nails that were connecting the brace to the block are transferring, and we have to make sure that they're able to transfer. Again, those nails that connect the brace to the block have to transfer the alpha R2 force. However, the alpha R2 force, once we resolve that and we see that there's a vertical component to it, it gets into this block. Well, what resists that vertical component of alpha R2? So let me use green here and see if I can kind of show you the idea. And I'm going to show it with a double-headed arrow because, again, it all depends on whether the brace is getting pulled or it's being compressed. That'll dictate whether the force is, the vertical component of the alpha R2 force is up or down. But we're going to say this is vertical. See if you can follow what I'm saying here. This is actually vertical, the vertical component of alpha R2 over 2. Do you follow why? Well, this block is connected to rafters on 2 sides, right? So it may not be exactly 2, probably is, probably pretty close to that, but you can argue that it may depend exactly on where the brace connects to the block. But in essence, what you have here is almost the block. You can model that as a little simply supported beam, simply supported on the left side by one rafter, on the right side by the other rafter, and then you've got this force in the middle acting up or down. concentrated force there, right? So you could argue that this reaction is the vertical component of alpha R2 divided by 2, as well as this one is alpha R2 divided by 2. So that vertical component goes into the rafter. You need to make sure that your rafters, that these two rafters are adequate for that additional loading that comes in from the brace. You also, let me get rid of one of these arrows. You also want to make sure that you have enough capacity in however you're connecting the block to the rafter. Now, one of the things that's covered in another tutorial is the nailing schedule that's provided in the IBC. So there is a standard nailing that if we as engineers do not specify any nailing there, any type of connector between the block and the rafter, the contractor will provide whatever is prescribed in that nail schedule. But if what's prescribed in the nail schedule, and let's just say hypothetically it's one nail, all right, one, and let's call it a 16D nail, whatever you want to call it, one 16D nail, and the capacity of one 16D nail, let's say hypothetically, is 100 pounds. If the connection, if the reaction that we need to transfer there is greater than 100 pounds, then what's covered in the nail schedule is not going to be adequate, and we need to provide greater resistance. If it is adequate, then okay, you can remain silent, and based on what the contractor will do in accordance with the table, with the standard table, then will be adequate. But we can't lose sight of that vertical force that we need to transfer from the block into the rafter. And once we get the load into the rafters, you know what, then it's, I don't know that I want to go much past this. You do need to keep in mind, if that rafter has uplift, you know, for this, let's say when it's acting and when the brace acts in such a way as it pulls the rafter up, depending on how much dead load there is resisting that uplift, we may need to provide upward resistance of the rafter at each end. But I think that's a matter for another tutorial if that's something that isn't clear to you. I think at this point, by taking the loads into the rafters, we can stop here and say that we've answered, and let me make sure of that. I'm going to clear all this and go back to the original question, which was what? What is the load path for the out-of-plane wind pressure on a stud wall with a parapet? I think we've covered that. Okay, so again, my name is Jeff Coronado. Here's my email address. If you have any questions on anything that I've said, please feel free to send me an email, and we'll try to take care of it.